In the second part of this video, I want to talk about normal and binormal vectors. And so let's start by thinking about the normal vector. So in the past, we talked about how to find the unit tangent vector, and that is our r prime divided by magnitude of r prime. And I have that drawn in blue. So the tangent vector is tangent to our space curve, just touching in the direction that the object is moving. The unit normal vector, or principal normal vector, is defined to be the derivative of our unit tangent vector, t prime, divided by the magnitude of t prime. And I have drawn in purple what that principal normal vector would look like. The normal and tangent vectors are always orthogonal. They make a 90-degree angle with each other. And the principal unit normal vector actually always points inward if the graph is curved, so in the direction that it's turning or curving, as I have shown in this picture. So let's do an example where we have to find and graph the unit tangent and principal unit normal vector at t equal 1 for the following plane curve r equals t squared 2t. So I'm going to start by finding my unit tangent vector. And to do that, I have to take r prime and divide that by the magnitude of r prime. So in this case, r prime is 2t comma 2. And so then the magnitude of that would be the square root of 4t squared plus 4. I'm going to go ahead and factor a 4 out of the square root. It turns into a 2. So I have 2 root t squared plus 1. So that means my unit tangent vector simplifies down to t over the square root of t squared plus 1, comma 1 over the square root of t squared plus 1. So again, to find the unit tangent vector, I take the r prime components and I divide it by the magnitude of r prime. And then I went ahead and canceled some 2's out. All right, so that's my unit tangent vector. Now to find my unit normal vector, I have to find the derivative of this tangent vector and divide it by its magnitude. So lots of calculus and algebra. So I use the quotient rule on the first component, the t divided by the square root of t squared plus 1. I used my quotient rule, and then I multiplied everything by the square root of t squared plus 1. To simplify, combined like terms in the numerator, and I was just left with a 1 in the numerator over t squared plus 1 to the 3 halves. I know I didn't show all those algebra steps. I'm really trying to focus on the new stuff here. If you do need help getting caught up with some of the algebra, let me know. I'm more than happy to walk you through those steps. And then for the y component, I actually didn't use the quotient rule this time. I just thought of the y component as t squared plus 1 to the negative 1/2, and then just directly applied the chain rule. All right, so there is my t prime. That's the derivative of my unit tangent vector, 1 over t squared plus 1 to the 3 halves, negative t over t squared plus 1 to the 3 halves. So that is the t prime. We still need to divide this by the magnitude of t prime to turn this into a unit vector. But because I'm done finding derivatives, I can start plugging numbers in. So you don't want to plug in any numbers until after you have found all your derivatives. But the t prime was the last derivative I had to find. So I'm just going to plug some numbers in. And so first of all, t of 1. So if I take, oops, go back. I guess we can keep all those numbers in. So first thing I have is t of 1. So I just put 1 into my unit tangent vector. So there's my unit tangent vector. I did that because I'm going to want to graph it. So there's t of 1. And then to find my unit normal vector, I'm going to take t prime of 1 and divide that by its magnitude. So I took t equals 1 and I plugged that into t prime, and I got 1 over 2 to the 3 halves. I decided to write that as 1 over 2 root 2. And then the y component was negative 1 over 2 to the 3 halves, or 2 root 2. Okay, so then we have to find the magnitude of t prime of 1. So I took the square root of each component squared, added together. I ended up getting square root of 2/8, so square root of 1/4, which was a half. And so then to get my unit normal vector, I'm going to take t prime of 1 and divide that by the magnitude of t prime of 1. So I took that t prime of 1, I divided it by 1/2. Dividing by 1/2 is the same as multiplying by 2, so I was able to do some canceling of some 2's. And finally, my principal unit normal vector is 1 over root 2, negative 1 over root 2. All right, so we are going to graph our unit tangent vector, our unit normal vector, and we're going to put that on a graph of this plane curve. So to finish this problem, I just jotted down my tangent vector and my normal vector. And then I'm also going to graph this plane curve. So our vector valued function is telling us that x is t squared, y is 2t. So I'm going to go ahead and eliminate the parameter. So if y is 2t, then t would be y over 2. And I'm going to go ahead and plug that into my x equation. So x is y over 2 squared, or y squared over 4. So we've got a sideways parabola. I'm going to graph that sideways parabola. And just to have some level of accuracy, I'm going to just plot a couple points. I definitely wanted to plot the point at t equals 1 because that's what we care about. So when t is 1, my plane curve is at 1, 2. So I made sure to get that in the right place. And then to help me find the orientation of this curve, I plugged in 0. So if I put 0 into my vector valued function, t equals 0, I get 0, 0. And so that kind of tells me what direction this is moving in. From 0 to 1, it's moving up along this parabola. All right, so there's the graph of my plane curve. And then I'm going to plot my tangent vector. So my unit tangent vector, here it is. The x component is 1 over root 2. The y component is 1 over root 2, so I tried to draw that in purple at t equal 1. And then my unit normal vector, it goes over to the right, but then it goes down. So over to the right, 1 over root 2, comma negative 1 over root 2. And feel free to convert these into decimals to plot that. That probably would be a little bit easier. But there's my picture, there's my graph. And so the thing I wanted to point out on the picture is notice that our tangent and our normal vectors are perpendicular, or you could say orthogonal. The principal normal vector is pointing inwards into the direction it's curving. Because this problem is a plane curve, we're in 2 dimensions instead of 3 dimensions. When we say two vectors are orthogonal, it's equivalent to saying they're perpendicular. And so what that means is notice that if you compare our tangent vector with our normal vector, the components are always going to be flipped, and one of the signs is going to be different. Let me see if I can actually write that down a little bit more formally for you. There we go. So if you're in 2 dimensions, if you have a plane curve and your tangent vector is given by some x of t, y of t, because your normal vector is perpendicular, you can actually just switch the x and the y's. Just switch the x and y's, and then one of them is going to become negative. How do you know which one's negative? It depends on the picture. That normal vector always points inward. We don't have, unfortunately, a shortcut for our space curves in 3 dimensions. We have to do all the math, and the math will tell us where that normal vector is. The binormal vector is defined to be the cross product of your unit tangent vector and your unit normal vector. And so together, the tangent vector, normal vector, and binormal vector form 3 vectors that are orthogonal to each other that move along the path of our space curve. And so I want to show you a picture of what that looks like. I'm going to go to a website to do that instead of trying to draw it by hand. I'm not actually going to do an example of computing the binormal vector, simply because I'm not going to ask you to do that in the homework. Homework is really going to focus on computing these tangent vectors, normal vectors, arc length, curvature. But I do want to show you a picture. So on this website, we're going to consider the following space curve. So here's an animation of the space curve we're thinking about. Okay, so coiling around like that. This space curve has a unit tangent vector. I'll show you what that looks like in red. So notice the unit tangent vector is tangent to the curve, and it's pointing in the direction that it's moving. So there's our tangent vector. And then our principal normal vector is in green, and see how it's normal to the curve, orthogonal to the, the tangent vector. And it's always pointing inwards, in towards the curvature. So then our binormal vector is orthogonal to both our tangent vector and our normal vector. And in this case, it's going to look something like this. Although I think it'll be easiest for me to show you if I show you what all 3 of them look like. So here is our same space curve. The red is our tangent vector. The green is our normal vector. And so then the blue is the binormal vector. And together, these 3 vectors are orthogonal to each other. So they kind of create this orthogonal coordinate system, you could think of it, that follows our space curve. All right, that is it for this video. I know it was a long one. Please let me know if you have any questions, comments, if there's anything I can clear up for you.